Welcome back, everyone, to the second invited talk of PQCrypto 2025. We're very happy to have Bas Westerban here with us today, who is the technical lead of the Cloudflare post-quantum migration. And I think it's fair to say that Cloudflare is one of the companies that are very far ahead of many others in deploying post-quantum cryptography. And we're very happy to have Bas here to share on what's the state of that now.
Thank you, Matthias. It's great to be back in Taiwan. This is my second time, and I think this is really a wonderful country. People are very hospitable. Thank you for the invitation. What I want to cover today is where we are and how we got here, and have a look at the challenges I foresee going forward. Also, I thought about maybe some lessons learned, but I thought that would be a bit too pedantic. Instead, I'll end with some PQ paradoxes. Okay. But before I get into it, I would like to thank you, because at this very moment, millions of post-quantum handshakes are being done every single second. This is actually quite recent. It's only a year now, and this couldn't have been done if you didn't start working on this many decades ago already. So, speaking for the whole of industry, I would like to thank you for all this work. Talking about industry. Cloudflare is a cloud company, which means some things are easy. It's mostly software, so I have very much a bias in the things that are difficult or easy compared to perhaps other parts of industry, especially people that need to create hardware have unique problems. So I'll try to mention some, but of course, as I don't work with hardware that much, I can't say everything. Okay, for those who don't know Cloudflare, we are best known as DDoS protection, so CDN. We have some other services, but this is not meant to be a sales pitch. What's interesting, maybe for context, is that approximately how you count that 20% of all websites use us one way or another, which accounts for about 15 million TLS handshakes every single second. We're very interested in improving cryptography and security on the internet, so we've been quite involved. We were one of the first to offer free TLS certificates. We worked on DNS over HTTPS, encrypted client hello. We're the second proxy in private relay, and of course, migrating to post-quantum cryptography. So from our previous migrations, we had already kind of a sense what this migration would look like. A good example is TLS 1.3. Oh, I'll get to that. We already, from previous experience, we knew that changing the internet and the web PKI would be hard. And there are two reasons for this. So the first one is that it's very diverse. There's phones, there's devices. Not everything is a nice desktop computer connected to fiber internet. Not everyone can update. Not every device can keep state. There's all kinds of weird configurations, and it's very hard to get visibility into it. Another problem is that despite thoughtful design, where our protocols are designed to be upgradable, in practice, if this protocol flexibility is not used, then it can happen that it's actually not implemented in the correct way. And you can't use the flexibility that was designed into the protocol. This is what I think it was David. I'm not sure who coined the phrase. It's called protocol ossification, where if you don't use the flexibility in a protocol, you lose it. So a good example is TLS 1.3. So TLS 1.3 was quite an ambitious effort to completely start over with the design of TLS. TLS 1.2 accumulated quite a bit of legacy, an enormous amount of cipher suites, a patch on top of patch, and they wanted to start clean slate. They started completely clean slate. The original versions of TLS 1.3, where also the wire format was completely new. Just start completely over, simplify everything. Security proofs, which was the initial version TLS 1.3 was quite beautiful, but also completely undeployable. The reason is that in TLS 1.2 you send the versions of TLS you support in TLS versions, and then if you support 1.3, then it would speak 1.3. But it turned out that quite a lot of middle boxes and servers, they just checked, do you support 1.2? If you don't support, I crash. Even if they should just, sorry, that's wrong what I said. There were a lot of servers that if they saw a TLS version they didn't recognize, they would crash, right? So even though you say, I support TLS 1.2, I support TLS 1.3, the fact that you say that you support TLS 1.3 confused a lot of middle box servers that shouldn't. I say a lot, it's actually not a lot, it was something like 1% or so, but even 1% is too much to make it deployable. So the way this was fixed is TLS 1.3 doesn't claim to be TLS 1.3. It says, I'm TLS 1.2. And it uses another bit of extensibility. So all the TLS 1.3 stuff is put into an extension. And for the rest, if you look at it, TLS 1.3 initially looks like TLS 1.2 on the wire. Okay. But eventually it worked. And it's a huge success. Now about 90% of all connections with us use TLS 1.3. Quick is essentially TLS 1.3. Okay, so migrating to post-quantum cryptography. For the internet, that will be 2 migrations. We have the key agreement to secure against store now, decrypt later, and we have the signatures to give authentication. The key agreement is urgent because of store now, decrypt later, and the signatures, they seem to be less urgent because we only need to be upgraded once the cryptographically relevant quantum computer is there. But it turns out that the signatures are actually much more difficult. All right. Key agreement. Because we expected trouble, we started testing with Google already in 2019. We actually tested, we tested 2 post-quantum schemes. We tested N3HRSS, which is kind of similar to MLChem, and we tested Psych, which, as you know, is broken now. The performance looked pretty good, at least of N3HRSS. It was hard to distinguish. But the big problem was that we saw a lot of trouble with protocol ossification. With N3HRS, the public key is thus large that it doesn't fit within a single TCP packet. So the initial packet would split into 2, which is allowed in TLS, but unsurprisingly, there are middle boxes and there are servers that got confused by this. So in 2019, Google invented this was called CSC PQ2, and they kept on. They ramped it up slowly, but then they couldn't ramp it up further because of these protocol ossification issues. I think that if we wouldn't have had these particular firewalls, which were particularly difficult, if we wouldn't have had those, I think we would have had a PQ key agreement deployed years earlier. So what we've been doing is especially Google has been reaching out. Whenever they ramped up, they got bug reports and they've been reaching out to vendors. They've been quite good at that. And over the years, when the number of reports started dropping, they increased the deployment until we are today where it's on by default. An interesting thing here, by the way, is that you would think that you would catch that these slow rollouts work, as that you get reports early. But there's a funny thing that the step before they went to 100%, they first were at 10%. And at 10%, they didn't get any more reports. And you would think, okay, then probably we got all of them. But once they turned on from 10% to 100%, they got a lot more reports. And which is weird, but it means that users, there was another particular firewall where users would, 10% of every connection would just not work. Or sorry, actually the way they rolled it out is that they enabled it for 10% of users. So for 10% of all users, this particular firewall would just, when they were on a network with this firewall, then for 10% of users, Chrome just wouldn't work. And only once we upgraded, when they ramped up to 100%, did we get the reports. So it was one of the surprising things to me that this happened quite a lot. People are able to deal with a lot of errors if it. By the way, feel free to ask questions in between. There's a button in front of you to enable the microphone. All right, so in 2022, after the selection of Kyber, before it was standardized as MLChem, we deployed a hybrid for production use. In 2023, Google enabled it server-side as well. And here you can see on the right the graph of the post-quantum key agreement, the amount of clients that support post-quantum key agreement, human-initiated traffic. So as you can see, last year it was only 2-3% that used post-quantum, and now it's about 38% globally. So Chrome and Chrome derivatives, such as Edge and Brave, have enabled post-quantum key agreement now by default. This is, by the way, a hybrid of X25519 and MLChem 768. Safari, that's the big missing one is iOS and Safari. We see that at the moment they are at 1-2% traffic. So I expect that Apple is very quiet about their plans, but I assume that they will not take long before they also ramp up by default. Go, programming language, and Zig already enabled post-quantum key agreements by default. Just today or yesterday, OpenSSL 3.5 was released, which enabled it also by default. And I think that this year we will see post-quantum key agreement enabled by default coming to a lot of libraries and software packages. I think if by next year, if software doesn't support it, it will be out of date, seemed backwards. Yeah. So as you can see, at the start that was Chrome Desktop enabling it, and later around November, the second spike up, that's Android and enabling it. So the interesting thing that why are these separate, you might ask. So the performance metrics on Chrome Desktop, there's a performance cost to it, particularly the bandwidth, but it was not that bad. On Android, they had the performance metrics were looking a bit worse, but so they required a bit more sign-offs to get it done. All right. So we were just talking about connections to us, that's number one, but we also have enabled support for post-quantum from us to Origin. So if you use us as a DDoS protection or CDN, we also connect back to the origin, to the customer. We don't just enable support there, but what we also do is we routinely scan what the origins support, primarily to... Oh. Oh, okay, it's back. So so we scan the origins, whether they support it. The primary reason we do this is to see whether we can safely enable it by default, because not all our origins are directly, not all our customer servers are directly accessible from the internet. So although all servers that get hammered now by Chrome will probably have the issue solved, that is not the case for all the servers that are configured with us. So we scan whether we can enable support safely. At the moment, only 1% supports PQ now. I think this will increase quite a lot over the coming year when OpenSSL supported by default, and when other clouds also support deploy post-quantum key agreement. As we see also the amount of errors we get, if we send a post-quantum key share immediately, about 0.34% crashes. This is higher, much higher than it is on the global internet. We reached out to help remediate, and we also asked customers what is your setup, right? Because maybe we can fix, maybe it's a bug in some known software package and we can fix it. But the annoying thing is that it seems that the issues are very fragmented. So it's very hard. We found a few big errors, but none of them. But the majority seems to be quite unique. For some, the setup seems to be quite unique, and there's also a long tail of weird bugs. Interaction between IPv6 atomic fragments and a kernel bug. Reordering of packets is also a problem. It's not just when it's split, but sometimes it's fine if it's in the order, but if it's in the wrong order. Also, an interesting example is where it will work if the server, if the SNI, so if the domain name of the website is in the first part of in the first packet, it will work, but not if it's in the second packet. So my colleague Suleiman gave a talk at PKI consortium where he goes into the different kind of bugs we saw, if you're interested. So up till now, I talked about the technical challenges, but that's quite a wrong impression to give, because the actual work will not be these technical challenges. For the majority, it will more be change management. So we also have internal connections where we need to enable post-quantum encryption, and that's actually took a lot more work. So in 2023, we started this migration, and this how to do it. It was a huge effort because we needed to email every single engineering team to ask them, hey, what services are you running? What connections do you have? Which software libraries are you using for it? And could you upgrade this? So actually, this is much harder than it seems. One thing we did is we sent every team, we sent them a nice little flow chart where it's like, if you use TLS, yes, okay, then you're in the easy part. Which library do you use? Okay, if you use this is the way to configure it. And the most common answer a question we got in response of this flowchart we sent out is from teams was, the first question was, how do I know if I use TLS? I mean, this might be that might be. You might think they should know, but if you have engineers, they usually just use some kind of library. They make a where whether it uses cryptography or TLS, it's just hidden behind layers of abstraction. So this is actually really hard. We upgraded quite a lot of connections, but a huge tail remains. It's just that this is not the highest priority for every single team, and it's, yeah. But we will get there. On the upside, on our internal connections, we didn't encounter any protocol ossification or performance issues. Okay, that's key agreement. It's urgent and the easier one. And with the adoption now, 38%, I'd say it's a new baseline of the internet. And that took 6 years. Any questions so far?
What sort of challenges did you run into in terms of protocol ossification when getting to 38%, right? It must have been a hard uphill battle.
Oh yeah, it's what I just, it's mostly the split client hello. So where the initial packet is split into two. That was the primary one. Yeah, but there are a lot of weird ones. So I had a link to Suleiman's talk at PKI Symposium, and there he goes in more detail to one of the weirdest ones. Yeah. All right. So the challenge ahead, the obvious one is signatures and authentication. So signature are much more challenging for several reasons. One of them is that more parties are involved. For key agreement, we just need to upgrade both sides. We just upgrade the TLS library on both sides, and it will magically do post-quantum key agreement. With signatures, it's not that easy. You have more parties to align, browsers, certificate authorities, HSM manufacturers, the certificate transparency logs, and every single server admin that cobbled together their own little script that writes RSA somewhere in a bash script. These all need to come together. And another problem is that it's not just a software update, but we also need to rotate the keys. It's also key rotation, and key rotation is one of the famously hard problems. If you want to embarrass a CISO, you should ask him when he last rotated every single key. The second reason is that there is no all-round great post-quantum signature scheme. So as you know, all of them have, so this is of the soon-to-be standardized, but also on the on-ramp, every single signature scheme has some kind of annoying feature, be it the size of the signatures or the speed of verification. So of the best of the worst is FNDSA, but we're quite uncomfortable using it in every use case because of the fast signing requires floating point arithmetic, and although Thomas Brennan is doing great work, I don't think I'm comfortable suggesting that everyone should just deploy FNDSA for online signing when it can be timed. But this is, of course, not a problem for verification, and it's not a problem for offline signatures. Another problem is that for key agreement, there's just one, it's only used once in a connection, whereas signatures, there's a lot of signatures on the web. Basically, every problem we had, we solved them by adding another signature. So there's obviously the handshake signature on the bottom. Then there's the signature of the intermediate on the leaf and of the root on the intermediate, if you only have one intermediate, but it can be more. You have two public keys, the public key in the leaf and the one in the intermediate. The root is not sent. And then there is also two SCTs, which, who knows what an SCT is? Yeah, so there's a system called certificate transparency, which after the big DigiNotar hack, which is one of the shameful contributions of the Netherlands to security. So the DigiNotar was a Dutch CA, which was hacked by Iranians, and they issued a certificate for Google.com, which was then used to man-in-the-middle Gmail. So Google detected this because they used public key pinning for their own domains. But public key pinning is not scalable. So instead, because of this hack, they stood up certificate transparency, which is a service run by multiple parties, where every certificate authority needs to submit a certificate they want to be trusted by browsers to at least 2 independent certificate transparency logs. To prove that, and these certificate transparency logs then publish them again. So this is the reason why if you go to crt.sh, you can look up all the certificates that have been issued. To prove that a certificate has been logged in certificate transparency, the certificate transparency log returns a SCT, a signature to prove that it was logged. This is the SCT. So every leaf certificate contains at least 2 SCTs to prove it has been publicly logged, which is a great system, but it's another 2 signatures. Then there's also OCSP staples to help with verification, but those are OCSP stapling is on the way out because short-lived certificates basically solve the same problem without adding a signature. Okay, five signatures and 2 public keys. That means that if we just use MLDSA 44, we add 17 kilobytes. If we use FNDSA for everything but the handshake signature, we add 8 kilobytes. So the question is this too much? We had a look in 2021 where we padded handshakes with some certificates, dummy certificates. And here horizontally, it's how much extra certificates we put in, kilobytes, and vertically, it's the slowdown. So it slows down TLS connections a little bit. If you look on the right, there's a bump at around 40 kilobytes. That's when the initial congestion window fills up and an extra round trip is required. So we have because our round trip time we are close to a lot of people. So our initial congestion window can be larger. The typical congestion window is a third of the size. And then the bump would not happen around 40, but the bump would happen around 10 kilobytes. So with typical initial congestion sizes, it means that that TLS handshake time should probably double. So with having deployed MLChem, Chrome got a sense of how much the extra data cost them. And in 2024, they said that 7 kilobytes is implausible unless a cryptographically relevant quantum computer is tangibly imminent. They also have a quote which I didn't include, where they say that they will not, that they do not want to deploy MLDSA certificates for the web anytime soon because of the size problems. Another thing which is interesting is we had a look at the typical sizes of how much data is actually transferred over a connection. So one common argument is that, well, most websites are pretty large, images are large. Probably the extra 17 kilobytes doesn't make a big difference. So we had a look at our quick connections, and we used Quick instead of TLS 1.3 because Quick is mostly browsers. And if we looked at our quick connections and the total amount of data transferred from server to client, including TLS, and that turns out to be, so half of the quick connections transfer less than 7.8 kilobytes. The average is much higher because there's connections that transfer a lot, but the median is 7.8 kilobytes. Also, the median compressed certificate chain is 3.2 kilobytes, which means that today, for us, more than 40% of the data transferred over 40% of the quick connections is already certificates, just for certificates. Right? So if we adopt drop-in MLDSA, that would be the vast majority of data transferred over half the connections would just be certificates. Okay, that sounds bad, right? This doesn't sound good. But the question is, how bad is it really? Does it really affect the end user experience? We think it doesn't look good, but we will run another padding experiment this year with browsers to get better statistics. The problem is, from our side, it's a bit hard to get good metrics. It's much easier for browsers to collect them. All right. So performance, of course, is one thing, but as discussed with the key agreement, the bigger worry, the bigger blocker is actually protocol ossification. And from our 2021 experiment, we looked at the number of connections that were failing horizontally. You would expect a small rise because the more you transfer, the more likely it is to fail. But there's two clear jumps at 10 and 30 kilobytes, which means that there are servers, that are clients or middle boxes that do not like it if you send more than 10 or 30 kilobytes extra. This is actually particularly problematic for. So there are some approaches for the migration where you put the post-quantum signatures. So you have something that looks like a classical certificate, but you put the post-quantum signatures in an extension, and that would be easy to use for migration. But this protocol ossification basically kills that idea, right? Because if you install it server-side immediately, you basically break everyone immediately. Instead, what you want is that servers install two certificate chains, one classical and one post-quantum, hybrid post-quantum. And then the client slowly ramps up, and then you can detect ossification. Okay, so I'd say it's not great, but also not terrible. I think it will not break the web. If the quantum computer is near, we will deploy this, of course. But the performance impact will delay adoption, and there's a real chance that a lot of people will get caught with their pants down, so to say. So what can we do? Well, as you know, NIST has a new competition for more signature schemes, which is in the second round now. There's some really promising candidates in there, but we need more time to see how the security evolves, right? We can't just hope that a new signature scheme will save us. Maybe some concrete instances. So Mayo and SNOVA, by the way. Mayo and SNOVA look particularly good because Mayo allows for a trade-off between public key and signature size, which is very convenient because the public key is not always in there. The public key of the intermediate, of the root is not there, and the public keys of the SCTs are not there. So then you can use one where the public key is larger, but the signature is smaller. Also UV for that particular use case looks quite good. SkiSign with sizes, it looks fantastic, but having verification times of 35 milliseconds, that's not great. I think there has been a lot of improvement. It's exciting to see the improvement in the isogenies verification times. If there's an isogeny scheme which has verification times of about a millisecond, then we'll go and test to see how it performs compared to the others. But I don't think they're quite at 1 millisecond yet. Okay, that's hoping for better signatures, which I say we can't do. We need a plan B. And there's a few ways to lessen the impact a bit. We can leave out intermediate certificates. So Firefox already ships with a list of all intermediates that are trusted. Chrome can do that too. And then the client can say, I got a list of intermediates. I got this list of intermediates, so you don't need to send it to me, and that will save us a public key and a signature. Another approach to save a few bytes is to use a key agreement for authentication. This is ChemTLS. This is particularly useful if the best chem is smaller than the best signature. At the moment, it's quite a big change, and at the moment it's not the lowest hanging fruit, but at some point it might become quite interesting. If the best. Can we get rid of that? Yes. If the best KEM is smaller than the best signature scheme. Then there is also larger, more radical changes on the table. So we are looking at something which I'll briefly talk about, which is called Mercury certificates. But there are other proposals. There's systems for key transparency that are used in messaging apps, and the systems that are designed for that, people are looking into applying these also for the web. So one of them is Starlit Jellyfish by Dennis. And these are really seriously being considered, which is something that wouldn't, such a radical redesign of the web PKI wouldn't be considered before the PQ migration. So that really puts new things on the table. So what is Mercury certificates? The idea is to make the common case fast. So instead of sending a whole certificate chain, we send an authentication path, a Mercury authentication path. So this only works if you don't need a certificate immediately, because you need to batch certificates to issue them in a Merkle tree. So that's one concession. And the second thing that's required is that the tree head of the Merkle tree needs to be sent to the browser some way. So the client needs to have some kind of trusted update mechanism to get the tree heads. So it only works. Another thing is that, and another choice in this particular design is that it only works for short-lived certificates. Okay, so if you can deal with short-lived certificates, you can issue certificates a few days in advance, and you have an up-to-date mechanism, which is the case for browsers. And then you can use this and just send an inclusion proof, which is only a kilobyte, which is actually smaller than the median 3.7 we have today for non-post-quantum certificate chains. And in case the browser is not up to date, it doesn't have the latest doesn't have the latest tree heads, or you have a website which needs a new certificate immediately, then we fall back to the old X59 plus drop-in PQ signatures we have now. So, signatures, less urgent, but the path is very much unclear. And I really worry we start migrating too late. Any question here? Yes, please.
Yes, so you're hinting towards my question actually that I had when you said tangibly imminent, right? So when cryptographically relevant quantum computer is that close, like we're talking what, a year or two, possibly? It took 6 years to migrate the easy case. Conservative estimates right now from BSI say, I think 11 years until we have a quantum computer, so possibly earlier. Is there even a chance that even if we start now that, you know, we would actually get all of this done?
I think that at the time, if there's a cryptographically relevant quantum computer, and if by that time we have upgraded half, I think we've done a really good job. No, I mean, it's a good point, and that's also, I'm really worried about drop-in post-quantum certificates, because people are not going to turn them on if it has a noticeable performance hit. So I want to turn on something now which does not have a noticeable performance hit, so that at least we can make progress. So.
Maybe a follow-up question. So I understand you don't want to turn this on now for everyone. Is there some way to prepare for this so that, well, once the quantum computer is imminent, you can basically flip a switch and turn it on?
Yes, we will add support for post-quantum certificates, but toggled off. We will add support for them when the certificate authorities have them, so maybe next year or the year after. But the problem will not be us, right? It will be, I mean, to finish this migration, everyone has to do it, right? Also your smart TV. And,
Sorry, can I ask a question, please?
yeah, sure.
In your case, have you ever considered hybrid cases, which means those people talking about using both classical and post-quantum, they want have a double security and so on. Have you ever considered that case? If so, what will be the cost?
Yeah, so the key agreement we rolled out now, that's hybrid. That's X25519 together with MLChem 768. With signatures, if we deploy it now, it will also be, if we deploy it now for everyone, it will be hybrid. If people are only going to turn it on when the quantum computer is imminent, yeah, then hybrid doesn't make sense. The cost of hybrid is not that high in performance because the classical cryptography is pretty fast anyway. The cost in hybrid is well, I'll get to that actually in one slide later, so please bear with me. Okay, that's signatures. But of course, signatures are not the key agreement to signatures. That's not all cryptography. There's more cryptography. It's really exciting to see that, especially in the last few years, there has been deployment of more what Sophie Schmick calls fancy cryptography, like to attain more privacy goals like anonymous credentials, OPREFs, etc. It's really nice to see that being deployed. But a big problem there is that for most of them, there are no great post-quantum alternatives. Last year, I started crowdsourcing a list of deployments of fancy cryptography in industry now, not just proof of concept, but actual big deployments. And there's here's a link where you can go and have a look at if you need any new projects to make something post-quantum. There's a nice big to-do list. Okay, so now I want to say a bit about our plans. So Mercury certificates, we are working on an experiment to do that by the end of this year, hopefully. So we're going to deploy this with Chrome by the end of this year. We're going to do a certificate size experiment. And I expect that we will have preliminary support for post-quantum certificates to origins, where we are our own CA, so we can actually do it now already in 2025. More broadly, predictions. I think before the end of this year, we will see post-quantum key agreement in almost every library and platform. Oh, well, major library and platform. I expect post-quantum drop-in certificates not before 2026, and that might slip. And they will probably be disabled by default. And yeah, the poignant question is, when will we see a fully post-quantum internet? And I don't know. I don't know. Okay. So that's on where we are in the migration and the challenges. Any questions here before I get to the more light-hearted part? Yeah. So, I mean, this one we already discussed. We want smaller signature schemes, but we can't wait for it. But still, I think there's no. Don't be discouraged if you design a smaller signature scheme. It will be used in the end, right? Another one, which you probably all know, is that some people say that every single CPU cycle counts, but it's just one consideration. Other considerations which are important is how easy is it for hardware people? How easy is it to mask? And that's one of the actually the hardware folk I talked to. Their primary complaint is that in the selection of the algorithms we have now, a little consideration has been given to how easy things are to mask. So next. Other one is how easy is it to implement? So if you look at the deployments, people generally don't deploy the very fastest implementation. They deploy implementations which are simpler, so there's less chance of implementation mistakes. Although slowly people will start deploying the faster ones. So these you know, but perhaps a paradox which is less clear is that a lot of people say we need options. We need to have this. We need to have a version with SHA-2. We need to have a version with SHA-3. We need pre-hashing. So you will hear a lot. We need options. But on the other side, industry really wants all kinds of different options. But on the other hand, we really can't be trusted with multiple options. And one, I mean, if some of these examples, if I discuss them, I'll get a lot of flack. But one of them that's not as controversial is the MLChem private key format. So that's a nice one to give an example of. So MLChem, the standard allows for two different private key formats. So one of them is a seed, which is actually not completely a seed. It's two seed values, a D, which is used to derive almost everything, and Z, which is used in the implicit rejection, and a semi-expanded format, where from D is expanded into ST row and the hash of T in row, where S is the secret vector, T is the LWE sample, and rho is the seed for the public matrix A. Well, the seed obviously has the edge in size, simplicity. And it's simpler because if you get a private key, if you get the expanded private key, the question is, what do you check? Do you check whether the cached hash was computed correctly? Do you check whether the coefficients in T are below Q or not? So having a seed makes that simpler because there's no question about the consistency to check. Then there are also some quite marginal security benefits. There's some binding properties of which attacker model actually is quite unrealistic, I would say. And you can't do a kleptography thing with the seed, whereas with the expanded you could compute rho differently and sneak in the original seed. Okay. So seed, I mean, it's better, right? When the draft was out, we suggested could we perhaps change the private key format from expanded to seed, and NIST they allowed both, which is a common thing to happen in standardization. If there are two options, very often both are picked. Well, for compatibility, this is actually the worst outcome to have both, because the difference between the two formats, I mean, it's not that big. I mean, it's only a few kilobytes. It doesn't matter that much. You might ask, by the way, why do you need a compatible format for seeds, for private key? Well, one example is if you have, for certificates, if you have your ACME client, your certificate bot of Let's Encrypt create for you and the web server reading it. So you need some kind of format. Okay, so what happened at the IETF? At the IETF, the question was, which one, do we allow both, or do we pick one of them? Originally, the feeling in the LAMS working group was to just stick with seed, but then on the last minute, there was a kerfuffle. 200 emails later, what we ended up with is 3 formats. So in X5 and 9, you can now use seed, expanded, or the both format, which includes the seed and the expanded format. Yeah. And the main reason why this happened is because there were already deployments of MLChem in the world that didn't support the seed format. So yes, post-quantum legacy is already real. Mike Onsworth he created a good jest. He created a sticker with "I fought in the Great Private Key War in 25." But this is really, it's not that consequential. There are choices which can be more consequential. Examples of this is hash MLDSA versus pure. So that's an example where, please, if you specify, just pick one of the two. Don't specify. Don't emulate NIST and specify both. Just one, please. And there's also a funny thing that these discussions only happen if the options are on the table. So for instance, in MLChem, Ketchup is used internally for derivation. No one has asked for that to be, well, during the design, during the competition, people asked for it to be replaced by something based on SHA-2 instead of Ketchup. But afterwards at IETF, there was no discussion at all, right? So if you don't give industry the options, then we won't make mistakes with them. So hashes. Another one is that there was a proposal to have 3 different signature formats for FNDSA, which, and of course, I think hybrids is the quintessential example of the problem of having too many options. I think that if I would go back and change one thing, it would be to put in the NIST call that also each scheme should specify a hybrid, a concrete hybrid, so that we don't have to do it. That's options. I have one more, which maybe, let's see. First, any questions?
We have some time for questions. Actually, quite a lot of time. So let me start with one question. So you've been very quick in deploying MLChem. So NIST just announced a new selection of HQC as their next chem standard. Are you expecting to also deploy this very fast, or?
So before the standards dropped, we actually wanted to implement them to see how well they performed in practice. But we're not in a rush to deploy HQC. The performance is not great, I expect. Yeah. And actually a question for you is, which I'm quite curious about, suppose MLChem is completely broken by some cryptographic attack. How likely is it that HQC is not completely broken? So if someone has opinions about that, I would love to hear it. Marco?
Well, as a matter of fact, the 2 schemes are very, very similar. I was discussing this with Ron Steinfeld, and there might be like a deep result connecting these 2, in our opinion. NIST says that it's a completely different hard problem, but on the other hand, you are just adding error and removing error and handling that. So we'll see.
Thank you.
Any more questions?
The room is full of actual cryptographers. Please comment on that if you have.
Any more questions or answers?
Surprising.
There's a question here.
Hi, so I had a question about certificate transparency. I don't know much about it, but how easy is it? Does it need any fancy cryptography, or is it easier to transition to post-quantum?
Certificate transparency, that's just signatures. So signatures doesn't make it easy for us, of course, but fancy cryptography is harder. So the one problem is, of course, the 2 SCTs in the certificate. That's one problem. Another problem is that especially if we all get on the URV train, that the size of the certificates will be much larger, which will be a problem for certificate transparency. Already now, the sizes are an issue. There are some approaches to solve this. There's a new... so one of the issues with CT now is that the API is not very cacheable, and there's a new variant of it. It's called static CT, where the API is more cacheable. That will make it easier to have bigger certificates in there. But a better solution there would be to replace the public key in the certificate by the hash of the public key. That work hasn't started yet, but that's another thing. Yeah. But for the rest, yeah, the sizes and the SCTs. So I think someone from after my colleague Luke gave a talk about this, someone from the NSA came up to him and said, why do we need to upgrade? Can't we keep the SCTs classical? Why do we need to upgrade those to post-quantum? So yeah, there's the problem with the worry there is that I think certificate transparency is very important, but there's also a good chance that it's being left on the wayside if we don't make it. Yeah.
So then a quick follow-up question. It seems like if you have certificate transparency, then for a lot of the certificate authorities, using a stateful signature is actually kind of solved by the certificate transparency, because if you screw up the state and sign twice, the law could reject it. Do you think that there's any room to push for something like this and just say, hey, NIST, forget the standards, we're doing stateful?
And that's actually a great idea. So CT logs, you can submit to any CT log, right? So the CT log itself doesn't need to know about other certificates, so it won't work as is. But one thing so people think that the state is part of the private key. It's used as part of the private key. So but if you think not of it as part of the private key, but as something that's apart from it, then other things. So one idea is to have just have a bunch of servers where you send your hash of your public key and ask, hey, give me the next 1,000 leaves which I can use for signing now. And then these servers, the nice thing, so keeping distributed state is a very hard problem, but in the case of stateful hash-based signatures, it doesn't have to be perfect. It only has to be monotonic, and that's actually easy. You just take the maximum of the things you think it could be. Yeah, so these approaches actually are being considered, yeah. But stateful hash-based signatures, if you look at the sizes, they're not better, they're worse than FNDSA. If you truncate to 128 bits, in which case you then, which is not standardized, and in that case you lose the non-repudiation, then it's quite similar. So non-repudiation means that if you truncate hash to 128 bits, I can find one signature that works on two different messages. Sorry. Anyway, the problem with then still, if you truncate to 128 bits and you don't care about the non-repudiation, then still the sizes are similar to FNDSA. So you have two different ways to shoot yourself in the foot, either with FNDSA or with stateful hash-based signatures, which I kind of lean towards FNDSA being a bit, yeah, I know, both are annoying.
There's no more questions. Any more questions? No? Then let's thank Bas for his great talk. Next up is